So we're given a differential equation and we are told that it is a separable equation. Separable means that we can group the x's together and we can group the y's together. So there is a way of writing the equation such that the x and the y's do not mix. So if I write that down again, the first step I do when I'm dealing with separable equations is to look for inaccessible parts of the equation. What I mean by that is, for example, the exponent here is x squared. The exponent bit of a function is rather inaccessible in that you cannot really do some manipulations there quite conveniently. And so if I have a function that is rather complicated in the inaccessible part of the equation, I'd like to make a substitution. So that's what I usually do to make things easier. So in this case, let's use the substitution u equals x squared. So again, the goal is to eliminate complicated functions in the inaccessible part of the equation. And so if we make the substitution, we see that the differential of u is just, well, the derivative of x squared, which is 2x, and dx. So that's the differential that we have. Now, if we write our equation, let's call our equation star. If we write our equation star in terms of du, so before that, we can actually do the following rewriting. So I'm just going to move the x here. And I think that's pretty clear to you why I'm doing that, but I'll just do it explicitly anyway. So here I did this grouping here because I noticed that that's very similar to this expression here. I just need a 2. And so I'm going to put a 2 here, but I don't want to change the value, so I'm going to also divide it by 2. So this term here did not actually change its value, but now I can substitute du for this term here. So that's just going to become du, and I still have my y cubed and my 1/2. And here, now I can substitute that with e to the u dy. And so this looks much easier than the previous equation. And we also notice that this is a rather nice form, because what I can do next is to just move one of them to the other side. So I'll just move the e to the u to the other side. And now we can see that we can actually divide the whole equation by y cubed e to the u. So I'm just going to write that explicitly here. I'm going to divide it with y cubed e to the u. And I'm also going to do the same thing on this side. And now what we have is 1/2 1 over e to the u du. Now on the other side we have du over y cubed. And to make the integration easier for us, I'm just going to rewrite it this way. So actually we missed a minus sign here. This should be minus here. Should be minus here. And this should be y. And if we just carry out the integration, that would look like the following. Plus an arbitrary constant. Okay, so if we just get rid of the minus signs and the 1/2, so we can actually multiply everything by 1/2. And we can get rid of the negative signs here as well. So that just becomes negative e to the u y raised to the minus 2 plus c. And the c here is different from the c here, but that's fine because they're just a multiple of a constant. So if I actually want to get an explicit expression for y, I can just move the c to the other side. And again, I'm not putting a negative there because, again, this c and this c will be different, but they are just constants. They're constant multiples of each other. So, and now what I can do is just multiply everything by y cubed e to the u, or rather y squared e to the u. And so what we have is e y squared e to the u minus y squared equals e to the u. And if I just want to isolate the y squared bit, I have e to the u over c e to the u minus 1. And this is getting closer to an explicit expression, but if you don't really require the explicit expression, now we can substitute back our x squared. Recall that we defined u to be x squared. So what I now have is y squared equals e to the x squared over c e to the x squared minus 1.